Hello everyone, I am Arvind for EC01009. So today I will be discussing about the lab 5. We have to study the application of fast Fourier transform for the analysis of signal. So to compute the pulse rate of the given PT signal using fast Fourier transform. In the last lab, we computed the pulse rate of PT signal using DFT and compared that result with autocorrelation. So today we will use fast Fourier transform for the same thing. And we have to extract the respiration information from a mixed signal containing PPG as well as respiration on Arduino as well as MATLAB using FFT and inverse FFT operations. So what is FFT? FFT is an efficient version of DFT. It is a divide and conquer method. Basically, suppose we have to calculate the Fourier transform of a given sequence. We reduce it to the Fourier transform of given sequence and Fourier transform of odd sequence and then process it later. So this divide and conquer technique reduces our complexity to n log n, and you can derive this complexity using the method of reconciliation where fn let fn be the complexity to solve for an array of length n. Fn is equal to 2 fn by 2 plus n. After solving this reconciliation, you will get the complexity as n log n. But we observed the complexity as O(n) square in case of endpoint DFT, which we implemented using matrix. So there are two types of FFT algorithms. One is decimation in time and one is decimation in frequency. In decimation in time, we divide the array in time domain, and decimation frequency divide the array in frequency domain. So here we will use DITFFT, decimation in time fast Fourier transform, where endpoints time sequence will be split into even number and odd number sequences respectively, such that Gk is the fast Fourier transform of the even sequence and Hk is the fast Fourier transform of the odd sequence. So, and recursively, these again are divided into even and odd. So, hence we obtain the improved complexity of n log n. So, FFT can be performed only if n is of the form 2 power n. As proved in the reconciliation, it should be in the form of 2 power n, so as to make the thing smooth, and if the samples are not enough, we will do the zero padding. So let's get started with our first question. So we have to compute the pulse rate of the BP signal using a 50 algorithm for given signal of duration 3 seconds. So in this lab, we will be using Arduino FFT library, which is an inbuilt Arduino FFT library. So double X is our input signal, BPD signal, and we have to take 128 samples because we are given 75 samples. We will pad it with the remaining zeros to create an array of 128 size, and our sample frequency is 25 Hz, and our SMS signal V real and V imaginary are the part of input signal, and XFFT is the output. So first we have done the zero padding in this section, as you can see. Now after doing the zero padding, we are taking the moving average of the same signal using window size of 15, and this is the code for FFT inbuilt library FFT.windowing. We are using Hamming window to first smoothen the signal again, and then we are computing the FFT forward using FFT.compute function, which is a part of Arduino FFT library. In this, V real is the real input part of the sequence, and V imaginary is the imaginary part of the input sequence. And samples denote the number of samples which are in our signal, and FFT forward denotes we have to calculate the Fourier transform. So now we have done the Fourier transform. We have to just estimate the peak of the Fourier transform so that we can get the pulse rate. Since pulse rate is the most repeating sequence in array, so maximum peak will correspond to pulse rate. So here we are finding the pulse rate of the sequence by comparing and getting the maximum of the sequence. So, and using this NFS by n formula to find the frequency and into multiplying it by 60 to get the pulse rate. So here we have calculated the pulse rate, and this is our inverse FFT array. This is our FFT array, and our pulse is 70.31 as calculated from fast Fourier transform. So now we are heading towards question 2. We have to extract the respiration rate from the given mixed signal using raw PPG and respiration information mode. Now, as you can see that this magnitude response of the FFT contains two peaks in the initial phase. One peak will correspond to the respiration part and another higher peak will correspond to the PPG part. Since respiration is also there, it is proportion of both respiration signal and PPG signal, so it will have respiration as well. But we know practically that range of PPG frequency is from 0.5 Hz to 5 Hz and respiration frequency is 0.05 Hz to 0.5 Hz. So what we will do is in Fourier transform we will nullify all the remaining part except from respiratory frequency, and then we will compute the inverse Fourier transform to calculate the respiratory signal and use that Fourier transform to calculate the respiratory frequency. So here is the MATLAB code. We have loaded the data. We have computed the first Fourier transform of the signal. Now we have omitted some part of the first Fourier transform, and after doing this, so this is a given signal. This is the frequency spectrum of the given signal. Now after skipping this part, because we don't want PPG signal, we have to deal with only respiratory signal. We have skipped this part. Now we will calculate the inverse Fourier transform of this signal to get the respiratory signal like this, and using this frequency spectrum of the respiration signal, we can calculate the respiration rate. So now get to the another question. We have to extract the respiration rate from a given mixed signal on Arduino program. In the previous question we did it with MATLAB program, now we have to do it with Arduino program. And we have to plot both PP signal and respiration signal to verify the correctness. So similar code, there are very few changes. We have imported Arduino library again, we have calculated FFT, we have omitted some part in this section, and we are calculating the inverse FFT. If k is in between, then we won't make it 0, as we will make it 0. So this means that we are only dealing with PPG signal here. So here we will get, so if k is not equal to 0, so we have calculated inverse FFT. So that's it. This was the respiration rate. Now this was the extracted PPG signal after nullifying that respiration part. After nullifying that respiration part, we will get the true PPG signal without any line of respiration signal. Now this is our respiration signal which we get after omitting the PPG signal part, and respiration rate is 18.36, which we calculated from the FFT part. Now that was all for lab 5. Thank you for listening.